starting to depixelate, and I'm looking right here. This is just going to be a really quick live stream just to give you some pointers for some revision things that you can be doing today for your second GCSE physics exam tomorrow. Basically, there's loads of links in the description. I'll go through those in just a second. This is mainly for OCR A, okay, and I'm going to go through just some really pointers on waves, nuclear energy, and then space, and some kind of hard bits and some kind of common mistakes that people get for those. And I'm going to talk about energy. And basically, in the description down there is loads of practice second paper questions. There's kind of 4 playlists. There's a foundation tier combined science, there's a foundation tier higher science, physics obviously, and there are 2 actually triple science papers there, 1 a live feed and 1 a set of videos, a playlist. Right, so go and find them, go through them, but when you go through them, focus on how do I solve the problems rather than what the actual answers are, because the questions will be different, but the way in which the problems are solved, that won't be different, okay? That is what they'll be asking you to do. Right, without further ado, let's just jump straight into it, okay? This is useful for all exam boards, but maybe if you're not doing OCR A, that's OCR Gateway, then you might want to, if you're watching this, skip past certain bits. Those playlists just skip past certain bits. I'll be live feeding about AQA stuff later this evening, so tune in for that if you are AQA. Right, so the first advice for waves topic is make sure you just get your keywords right, okay? So there'll be lots of description type of questions there. There will be some calculations normally around the wave speed equation. Wave speed is frequency times wavelength, and make sure that you use meters and hertz there. And make sure that you can use the times 10 to the button on your calculator, so you can use very large or very small numbers because you have very high wavelengths, very short wavelengths, very high frequencies, very short frequencies. And so we use times 10 to the something to simplify those numbers. The calculator understands it if you press the number times 10 to the, and then whatever the power of 10 in that number is. You just treat it like a normal number. So make sure you can use that equation. Obviously, with regards to equations, then all of the equations from your equation sheet can be used in the second paper. Don't delineate, say this is not going to be used. So make sure you prepare for that. They're unlikely to ask you about density, for example, but they could well ask you about thermal energy. Also, make sure you can do ray diagrams. Thank you. You make sure you can do ray diagrams. Ray diagrams being where you've got the axis, and you've got an object, and you've got a lens, and you can construct them. Practice them because they're really easy if you know how. You're not going to get it if you haven't actually revised that, so make sure you practice them. Next bit, okay, nuclear physics, okay, make sure you can do nuclear equations. Again, they're really easy nuclear equations because you just need to make the top line and the bottom line balance. As long as you know the code for alpha, 4 and 2, 2 protons, 2 neutrons, the beta, -1 and 0, 0 mass, -1 charge, and for even a neutron, 1 mass, 0 charge. And just make the top line and bottom line balanced. You can do that. That's a very simple, straightforward question. Half-life, there's a lot of common misunderstandings about half-life. Okay, and the main one being that, well, firstly, that it's not a time, it's just whatever half of the activity is. So you typically half the activity and you use the graph to find the time taken for that activity to half. It could be the number of radioactive nuclei to decay, or it could be the activity. But you half the y-axis, go across the line and down to the x-axis, but you're always looking for a time. The other confusion that people have is that if it takes that amount of time for the first half to decay, it takes that amount of time for the second half to decay. That's not the case. It takes that amount of time for half to decay. So we just keep on halving and halving and halving and halving. So you get a half, you get a quarter, you get an eighth, you get a 16th, and so on. Okay. And then lastly, quantum. Okay, this idea that when atoms absorb energy, a photon of energy, they are raised up the energy levels. Okay, and when electrons fall down the energy levels, then they release a photon. This is a new idea, and they've got this absorption and emission spectrums. Make sure you know the difference between them, make sure you can explain them in terms of energy levels, electrons going up for absorption spectrums, electrons coming down for emission spectrums. I think they're going to be using those in tricky contexts to do with wave calculations, maybe, to do with space and Hubble's law. Okay, so make sure that you are au fait with understanding what those different emission and absorption spectrums actually show. Next one will be energy analysis, and that's a huge bit, and I'm getting this down, okay, because it's a big change from the previous one. So if your teachers have taught this to you, they may not have been referring to what we expect to see in the exams. We expect to see you talking about 8 stores. Okay, learn the names of 8 stores: the chemical store, the thermal store, the kinetic store, the gravitational store, the elastic store, the nuclear store, the electrostatic store, and the magnetic store. We want to read, basically, in an energy transfer, one store has 2 stores, your store if you like, and your final store, and then identify how the energy gets from one store to the other. There's only 4 transfers, right? The 4 transfers being mechanical working, so that's by forces, electrical working, so that's by currents and potential differences, heating by particles, so that's conduction and convection, particles knocking into each other basically, heating by radiation, so that's electromagnetic energy transfers, if you like. Right, okay, and then, so not only do you need to think about those 2 stores and how it gets from one store to the one store increasing, the other store decreasing, okay, you need to think about the equations, because energy analysis, the basis of this energy analysis is using one type of energy to calculate with another type of energy. So it's about making 2 energies equal. So I've got some kind of typical examples. So here's some equations. I'll go through them just in the order there. We don't have an equation for chemicals, so you're not going to be asked to calculate with a chemical store. We do have an equation for a thermal store, though. The thermal store being E is mc delta T. So this is mass times specific heat capacity times temperature change. And it could be also mass times specific latent heat as well. They could ask you to use that. That's given on the equation sheet, that one there. So you could be asked to use with that. The kinetic store is half mv squared. So learn and refer to the equation half mv squared in the exam. The gravitational store is mgh. Gravitational potential energy is mass times gravitational acceleration times height. Then the elastic store is a half k delta x squared. Okay, so elastic strain energy, a half times the spring constant times the extension squared. Nuclear, there is an equation for nuclear, and you might want to refer to it in an explanation, but they're not expecting you to calculate with that. E equals mc squared, and then E equals VIT for the electrostatic or electrical store, so VIT. Voltage times current times time, power times time, in other words. And then lastly, magnetic, and we don't have an equation that we want you to use for that one. Now, the key to energy analysis, as I said, is working out one type of energy and making it equal to another. So, for example, in a specific heat capacity experiment, we work out the energy we've transferred to the heat electrically, and we make it equal to the thermal energy gained by the block. So you can basically write yourself an equation, VIT equals mc delta T. And then you can plug in all the things you know, and you can work out an unknown. Or another really common one would be you raised a ball up in a gravitational field, and then you've dropped it, and it's got kinetic energy. So you make mgh equal to half mv squared. Put them together like so, and you've got mgh equals half mv squared. And actually, there's a useful thing here because the mass is the same on both sides, so you can just cancel the mass. So that's a really common one. It could be the other way around, though. It could be that something starts with speed and goes up. How high does it get? Half mv squared equals mgh. It could be you've used a catapult, okay, so half k delta x squared, and you make that equal to half mv squared. So you've pulled back, extended something, it's gone back to its original shape, transferring, or the elastic store decreases, the kinetic store increases, make those 2 equations equal to each other, and you've got an equation where you can work out the speed. So that's the basis of energy analysis, right? So I would look through your revision guides, your textbook, whatever, and look for the kind of common equations that they make equal to each other, and make sure that you could rearrange that. Okay, next bit to chat about is, I'll just talk briefly about advantages and disadvantages of energy sources. Now, loads of you are going to learn loads of detail about the different energy resources like wind, solar, nuclear, coal, all these different things, right? And you're going to learn all the advantages and disadvantages. And when you see that, and you see something like, tell me some advantages or disadvantages, you're just going to bang down your set list, right? But what they're going to be doing with you is they're going to be giving you a context. They're going to be talking about somebody somewhere wanting to build a power station of some kind, and you have to get advantages and disadvantages that are relevant to that context. So make sure that you do that. Next one is, with global challenges as well, they talk a lot about stopping distances, which are braking distances and thinking distances added together. And the thinking distance is proportional to speed because the thinking time doesn't change. Okay, so the faster you were going, and you're not slowing down the point, so the faster you were going, the faster the speed, the faster you were going, the longer the thinking distance will be. But braking distance, you have to dissipate kinetic energy, and kinetic energy is equal to half mv squared, so double the speed, 4 times the energy. So actually double the speed, quadruple the braking distance. Okay, that's the key point that they're looking for there. Now also with that, with all that road safety stuff, they like you to use the equation v squared equals u squared plus 2as, or v squared minus u squared equals 2as. And just think about that. A lot of the time you might know what a is. You might know that a is equal to g, so 10 meters per second squared. Or you might know that an initial speed or a final speed is 0, because I'd have said something comes to a stop, or starting from rest, something like that. So make sure you can use that equation, v squared equals u squared plus 2as. Then more about the energy stuff, okay, the national grid. So the national grid is really about trying to avoid power loss. Power loss is I squared R, okay? That's the equation you need to remember for that, I squared R. In other words, power is proportional to I squared. A small increase of current, a very large increase in power loss. Double the current, 4 times the power loss. So we want to reduce our current. So we use transformers to increase the voltage into the power lines, and that reduces the current in the power lines. Okay, so make sure that you say that, and it's an energy loss due to heating. Literally, there's a friction between the electron and the ions. They collide with each other, causing a heating effect. And that heating effect is really important for explaining why we use transformers in the national grid. So get relevant equations, get a relevant explanation in there, talk about the heating effect of current. Now also with that, we talk about mains electricity being 50 hertz and 230 volts AC supply. You need to memorize that. We use AC because we have to use the transformers, right? And in our plugs, we have 3 different wires. We've got the live wire, which is the only one that changes from positive to negative, the neutral wire, which stays at 0, the earth wire, which is at 0, and the earth wire, remember, is a path of very low resistance, and it works alongside the fuse. When the fuse breaks, because it's got that heating effect due to current again, then the current will flow through earth rather than through the user. Okay, so fuse melts, breaking the circuit, current goes through a low resistance path to earth. That's the type of explanations there. And then lastly, make sure you learn really lots of detail about Hubble's law, life cycle of stars, and this idea of there being a kind of peak wavelength, which the hotter the star is, the lower the peak wavelength is. The lower the peak wavelength is, the higher the frequency is. So think about your electromagnetic spectrum again. Think about the highest energy end being the bluer end. The hottest stars have bluer light. They have higher energy light, okay, that they give out. They give out all wavelengths, but they have a peak, they have a maximum intensity in the bluer end, the higher energy ends of the spectrums. So make sure that when you learn those things, you learn them in really, really good detail today. Well, that's it, that's my chat basically. Do stick around. I really want to hear after your GCSEs how you do, so stick around, stay subbed up. I'll do a little live event on results day. I'd just love to hear how you all did, whether it was helpful or not. Stick around afterwards, because this channel is going to become more about the kind of process of learning, and I want to kind of challenge myself next year to actually take chemistry A-level. So that is a kind of little bit of a idea that I've got to put myself in some people's shoes. So maybe that would be useful for you. And also, as I said, lots of stuff in the descriptions down there, lots of stuff in the descriptions which are going to help you out tomorrow for your paper 2. Focus on, when we go through those exam questions, focus on how we solve the problems. I've also got a playlist for waves, radioactivity, energy, and space, okay? Right, awesome squad. Really pleased with you all, so nice to see you all. I'm glad you're doing A-level physics next year, Nathan. Okay, Andy, I'm not going to go through the equations really quickly again, okay, because luckily this is a video. It's basically, if you can actually rewind this now and go through that equations section. Okay, so just take your time. You can rewind back to the start of the video if you joined it late. Make sure you're subbed up. Tonight I'll be live again, okay, doing some mainly AQA stuff, but it'll be relevant to all exam boards. On my channel, there's loads of GCSE sections, loads of GCSE videos, loads of past paper questions for all different specs. So spend the time. Obviously, don't do things if they're not on your spec tomorrow, but make sure that you do work hard today. Also, this evening, don't overstress it. Make sure you get nice and early to bed, and make sure that you have quite a relaxed evening where you're just kind of reinforcing those key ideas, making sure you memorize the equations, making sure you've got the key ideas of energy analysis and all that kind of jazz. All right, thank you very much. Have a lovely day, work hard, and look forward to this. Most of you, tomorrow evening, okay, the 15th of June, the best day of the year. It's not only the end of your GCSEs for you, but it's my birthday, all right? So why not just pop up and say, happy birthday, Mr. Masters, happy birthday, Kit, tomorrow. Okay, it would be nice. And, well, pop up and let me know how your paper went, because I'm really interested. That's why I'm here, that's why I'm doing this, and trying to help you guys out. All right, that's enough. All the best.